we solve the system y prime equals matrix 1, 2, 2, 1, y. We assume that y is e to the lambda t times some x1, x2. And we then skip to the, we got the 3 dots. We skip down to here, the steps that I recommend that you understand so you'll understand what's going on. But if you want to just get the solution, you skip to this determinant, the determinant of a minus lambda I is going to be equal to 0, and whatever values of lambda you get are going to be eigenvalues, and we're going to be able to find x1, x2s that go with the e to the lambda t and give us a solution. So the determinant of this matrix is, as we see it, it factors, and if you can't factor it, by all means just use the quadratic formula if you're having trouble with factoring. And we get lambda equals -1, lambda equals 3. Lambda equals -1 eigenvalue corresponds then to a minus lambda I e to the lambda t x1, x2 equals the 0 vector. And again, that's part of what's in the dots here. But that tells us then that a minus lambda I times the x1, x2 vector has to equal 0, 0. We don't need the e to the lambda t in order to find our x1, x2. We just divide both sides by the e to the lambda t, and it works out. Okay, and there's stuff that goes with that you really have to understand about matrix multiplication and so forth, but it works that way, just like an algebraic quantity. It'll divide out. You have to prove that. You should know how to prove it, but it works. Okay, so now we have a minus lambda I times x1, x2 equals 0, 0. So far, this applies to either eigenvalue, but we're calculating for lambda equals -1. And that then gives us the a minus lambda I matrix becomes this 1 minus -1. Got a little sloppy there. Because right here is the matrix, right? 1 minus lambda. If lambda is -1, becomes 1 minus -1. And then we have the 2, and the 1 minus lambda, which is again 1 minus -1. Well, 1 minus -1 is 2, so the matrix becomes this. So we have the matrix equation that you see here, and it just translates to the system 2x1 plus 2x2 equals 0, 2x1 plus 2x2 equals 0. As must happen, this equation is just a multiple of this one. Turns out it's really an easy multiple. It's a multiple of 1. It's the same as the equation. But whatever happens, this equation will be a multiple of 1, assuming you have 2 distinct eigenvalues and so forth. That's kind of what you look for. Okay, so the solution then is x1 equals -x2. Now, we can express the solution that way anyhow, which means that we can choose any number for x2 and we'll get a number for x1. So we choose x2 equal to 1, x1 is -1. And now we find that our y1, our first function, first column vector function, solving this equation is e to the negative lambda t times x1, x2. Lambda equals -1. E to the lambda t is e to the negative t. And as we just saw, if lambda is -1, then the x1, x2 vector is -1, 1, or some multiple thereof. So that our basic solution that we're going to use is y1 equals e to the negative lambda t times -1, -2. Now we can use any multiple of that, but that might be the simplest multiple we want to use. So this, of course, is what? We multiply through, we get negative e to the negative t and e to the negative t. And that's what I've written here. We'll see why I wrote that. So that's one of our solutions. Our other solution is going to be obtained in the same way for lambda equals 3. And I can point it out, if lambda is 3, then this is -2, 2, and this is 2, -2. Yeah, -2, 2, 2, -2. And we easily get solution where x1 equals x2. We just go through the same process. We're going to have 2x1 minus 2x2 equals 0, meaning 2x1 equals 2x2, so x1 equals x2. The second equation is just the same as the first, but with opposite signs. It's -1 times the first, a multiple of the first, gives us the same result. So we can use x1, x2 equal to why did I do that? Oh, okay, I get it. Okay, we choose, so here it is. Actually, I did write it out. Here are our equations. X1 equals x2, so we just let x1 and x2 both be 1. So that our second solution is e to the 3t times 1, 1, which is e to the 3t, e to the 3t. That I've written here. The negative e to the negative t and the e to the negative t. From this one, I've actually written here. It's different here. This is a different matrix. I wasn't careful when I said that. Anyhow, this is our psi matrix. Our psi matrix, our solution matrix, has our two linearly independent solutions as column vectors. Now, I just said linearly independent. How do we know that this solution and this solution are linearly independent? Well, if we really understand linear independence, it's pretty easy to see that there's no way a constant multiple, a sum of these two by constant multiple, a sum of constant multiples of these two columns could give us 0 unless both constant multiples were 0. And you should understand how that's related to linear independence. It's a definition. And that's ensured if the Wronskian of this thing is not 0. So we calculate the Wronskian very easily. It's -2e to the 2t. And since the exponential can't ever be 0, this is never 0. Not only is it not identically 0, it's never 0. Of course, that's kind of the same thing. Okay. Well, this then is our solution matrix, a matrix consisting of linearly independent solutions, a square matrix consisting of linearly independent solution vectors in the columns. Since it's a square matrix, the number of rows has to equal the number of columns, and the number of columns equals the number of columns in the original equation. Okay. Actually, the number of rows in the original equation, but they're the same. Okay. So, I want to claim that psi is a solution to psi prime equals this same matrix times psi. Okay. Well, that's very easily done. We just take psi prime, take the derivative of this matrix, you can confirm that it's this one, and that should equal this multiple of this matrix.